open up the files, there is this day3-2 detection RMD is what we are going to use. While you are doing that, I think there were some other questions, comments.
Yes, I just wanted to just before someone, I don't know if this is true, that's why I'm asking. Someone said that this framework comes from like the physical realm, from physics and from the modeling gases in a confined space.
Mm-hmm.
So we are actually what we are doing is borrowing a concept like particles in the space. So we use like the individuals as they were molecules or something. But so the first one is if you have any comments about that, if it's and the second one is that like just what you said, but the assumption that molecules in the space like gases are moving randomly, but species or individuals are not. So for physicists that might work, but for us it might not. Yeah.
So these assumptions really think that individuals don't move and they are randomly distributed. And that means if we randomly put out nest locations, then they're just going to be glued there. And that's how we imagine this whole process happening. And so when I was referring to the non-random distribution, I wasn't imagining this to be like a dynamic system where you have these gases moving around. So when individuals move around their nests, that is more still in a confined space, assuming that they have some territorial behavior. So they are not just kind of doing a random walk and go from Edmonton to Calgary after some time, but they kind of just stick around. So how the movement is specified in the simulation is that you have some kind of two-dimensional kernel, which is just going to dictate which points are more likely to be taken if you kind of move around. And they can also put some constraints around their movement using tessellation, whether they are able to cross to the neighbor or not. So whether their home ranges can overlap if they're close together. So these are the types of things we are going to use in simulation, and how realistic they are, that's a question. I think to these kinds of sensitivity analysis that we are doing, it's okay. But if you want something more, I think then you need to extend these concepts and analysis. And then also, why we can't really do a lot of details in these models is something you're going to see. If you simulate, you know a lot more than what we can actually observe in the field. And even that information comes in bins. So we don't really know the exact distances. So it's even harder than for removal sampling, where you can kind of look at recordings and then have exact seconds or milliseconds when that individual was detected. This is much harder in space with locations, unless you have like triangulation and lots of detectors operating synchronized in a grid, or you can measure detections really precisely with rangefinders. If you have like whales and large mammals, you often get exact distances, but with birds, that's rarely the case unless you have a really small system that you can study in detail. But these point count surveys that we talked about, that they happen over large areas, this is often unfeasible. So that's why I think the data limitation kind of dictates the simplicity of the models that we are going to employ.
Thanks.
Yeah, we have a couple more questions.
Sure.
So Chris is asking how the error in estimating distance or distance bands could affect inference. So how delicate that assumption will be that the distances are accurately assessed.
You are going to see that for yourself. Binning can reduce it to some extent if you can say, well, shorter distances are better estimated, because then you can say, is it 50 or greater than 50? And if you are much better at judging what's 50 than judging at what's 100, then I think this has some merit, and this is often done in bird point counts, that we don't really have a lot of distance bins. We only have 2 or 3, sometimes more, but then that is what you start questioning. Oh, do they really able to just estimate distances so precisely? So when we looked at the data, we found that the binomial version, when you only have 2 distance bins, is a data that is much more commonly available than more than 2 bins. So I think that reduces that variation, which would be much larger at greater distances, but that's true. So I don't really have a simple answer to this, but we are going to play with this error. And that is, again, going to come as the not the detection itself, because whether you hear it or not, that depends on the distance and your ear. And then what distance you assign to that information, that's going to be more like how you perceive that. So that is going to be in a different layer, but still we are going to play with that, adding some measurement error to the distance estimation, and that causing misclassification in the distance bins, and how that affects our estimate of tau and the related population. All right, any more questions?
Yeah, I believe we do have. Jonah, do you want to?
Yeah, I had a quick kind of practical clarification I wanted to make around calculating or like estimating effective detection radii. So correct me if I'm wrong, but my interpretation is that it's the distance at which the proportion of individuals that go undetected within your truncated radius is the same as the proportion of individuals who are detected outside the radius during the point count. So just from a practical standpoint, like if you wanted to calculate a species-specific effective detection radius, how do you figure out the proportion of individuals that go undetected within your radius?
Well, that is something you don't know, but based on this logic, if you find this distance, then you know how many you detected outside.
Okay.
Right? Like given that you calculated.
I think I was probably caught up in a different part of the kind of the loop.
So this concept is really useful when you have an unlimited distance, and say you count things inside, and then think, well, you are really not counting these exact distances inside and outside, but you count some predefined distances, and within those bins how many individuals you get, which helps you to capture this curve. And if you know that parametric function of the curve, that gives you the ability to be able to then say which is the distance.
Okay, that makes a lot of sense.
Yes. So that's not something that you calculate, then go out and classify individuals.
Okay, right.
That distance.
The part that was or that I was stuck on seems to be, how do you figure out how many things you're not detecting?
Right. No, that's something you figure out not before you go into the field, but once you came back and you have the data, then you fit a certain model to it. And in half normal, this just happens to be tau, which is that one parameter you need to estimate. For other distance functions, this concept still exists, but there is a less straightforward way to get this quantity. You need to do kind of some integral and then figure it out. Or maybe there is a nice math formula that you can apply, but that's a bit beyond me. I just know half normal works. This is how. And for the rest, I can just use programming to get that quantity. We are going to talk about that because it slightly differs also if you have truncated distance count versus unlimited, and how to get that value using a function in R. That's really straightforward, although you need it really infrequently.
Okay.
All right. Let's then open this file up and start running it with loading some packages and datasets. I haven't updated bsims, so you don't need to update anything if you have that working from last week. Plink Plink is the mnemonic I got for today. So let's look at distance functions. This is just the same kind of review of kinds of detection functions that we had as part of the slides. So if you want to recreate those images and look at how we calculated that this is the code corresponding to that. So it's really straightforward because we set up a sequence of distances between 0 and 1 with 0.01 increments, and then plot these distances as a function of the distance function itself, which is just following the math, e to the power minus d over some parameter 0.8. That is going to look like this. That's the negative exponential. Now using the same 0.8 as tau, but now minus d over 0.8 squared. This is our half normal. And then same thing with some b equals 4, so to the power minus b. That is going to give us this hazard rate function. Now we can open up another little shiny app. Where we can much easily play with these functions, and we can say, let's increase tau to 2.2. Then you can see it becomes flatter. So if you want to look at larger distances, you can increase this R max, let's say to 10. And then you can see how increasing this, the variance of it is impacting the shape. And you can copy this function, distance function, which takes parameter distance and tau. So whatever tau you want to specify for simulations, you are going to need that. Or actually, the simulation is going to provide that. And then we can also take b to be 1, which is our exponential. We can make b to be something else. If we make it 0, that's just a flat line. That's probably a really bad distance function. But we can also increase it, which then becomes very similar to kind of a hazard rate, but just looking at it from upside down. So if we, instead of that, look at the hazard rate, then you see shoulder is up here. You can increase the variance, and you just see that it kind of moves from left to right and back. And if you change the b value, then the shoulder becomes less pronounced, right? So if you copy this from here, then you can use the exact distance function that you saw here as part of the simulation, because then you can provide this distance function, and this is how the data is going to be generated. Then you can see how you can estimate that if you assume something else. All right, so I'm hoping you're playing with this app the same way as I did. And let's do then some simulations. Again, with bsims, we set this tau a parameter, which is EDR for half normal. Otherwise, it's just the rate at which it decreases with distance to 2. Then we also set the seed so that you and me are getting the same numbers. The layers must be familiar. We create a simple landscape, no road, no edge. Then we populate it with a really, really high density. So density equals 10. That's just going to give us 1,000 individuals or more. And then when we animate, which is when we add the behavior layer to it, then we say initial location equals true. What this does is we are not going to have any kind of behavior influencing which individuals are going to be available for us to detect, but this is just going to make every individual in the landscape equally available. So this is a way for us to say P equals 1. All the population members are available to us. So this is a way to say we are not interested in behavior and availability. We're just looking at distance sampling. And then at the end, we use bsims detect. B, this is our object from before, and specify tau. This is what we are going to use in a half normal detection function for the parameter. So at the end, we get this bsims detection object, no stratification, 1013 individuals, no events, 10 minutes duration, and then we heard 128. And if you plot it, then this is what you're going to see. We have this landscape. Crosses indicate the nest locations, and there is no movement involved right now. So the individuals are just at these initial locations, and everyone is available. And these rays from the center, so if we don't specify any offset for the observer where he or she should stand, then it's just going to be put in the middle so that we are not cutting it off if you don't have a good enough buffer around it. So the rays are going to connect the observer to that individual that it happened to detect. And you can see that there are a lot more closer to the observer, a lot fewer at larger distances. So this is the kind of information, how many are coming from the different distances, that we are going to use to estimate the parameter tau. So now let's see what distance sampling is doing. First of all, we need to define these two functions, which, as you recall, g of d, this was the distance function, and h of d, this is just the size of the increasing circles. These were the two quantities that we multiplied together. So we have these three lines: the distance function, the frequency of the different distances, and the two multiplied together. So these were the three curves on top of each other. So this is that product of the two functions that we are going to work with. So let's get all the distances. So we have the A object, which is just this one, when we populated the landscape. So we have the nest locations, X, Y, that's just where they are. So we calculate this dA, which is going to be the distance. Summary. So this is the distance to every location. We can also show, all at once, how these look. So this is what we are trying to capture with h of d, right? So we have all these nest locations, and if we calculate the distances between the nest location and the observer, you can see they're a lot more farther away than close to the observer. And this is what we would expect based on the triangular distribution, the red line. And we can see the simulated distances follow this line pretty nicely because we didn't specify anything else. So the random distribution, how these nest locations are put out is, if you think about the two axes, X and Y, for each of these, independent of each other, we just pick a random number within the extent of the landscape. So it becomes uniform X, uniform Y, which is going to lead to a random Poisson point process. So this is what our random distribution is really doing, but we can change this to a more clustered or a more systematic distribution, and then this histogram is going to look slightly different. Then the other thing we need, so we have all the locations, and now we need just the detections. So this is coming from that O object, which was at the very last line. We did the, like we said, this is tau that specifies the distance function. Let's detect some of these individuals. So if you now print out this DT object, which is a data frame, you just pulled out the detections, and you can see the location, time, which is irrelevant for now, and the D. So this describes the distance from the observer. And this I and J, this is just the individual ID, and J is the perceived individual ID. That's what we were playing with last time when we had under or over counting. So this is what we had from the detections. So we can look at the distribution of values in the column D, which is going to give us this. So now we can take the total number. So that's going to give us that constant we need to kind of bump up the curve to have a real probabilistic meaning to it. And then we combine together the distances with the availability. So if you do this, then you get this distribution, which is the distribution of our observed distances. And if we know the distances, like the exact distances to not only where we had the detections, but also to the distances where we didn't have the detections. So for example, when you're doing an experiment and you have control over the distances and you are only interested in learning whether the observer could detect it or not, then it's much easier to fit any kind of model. And this is what we did here. And I'm not going to explain it in details. I'm just going to highlight that is the information we don't have. Because if we had the distances for the non-detections, then we wouldn't need distance sampling. We would just fit a binomial regression to it. So we have detections, non-detections. The true and the estimated curve are almost identical. It's very easy to just go with a simple binomial regression or just fit any kind of fancy curve to it. But the problem is we don't have the non-detections. We only have the detections. And so that's why we need distance sampling. And there is a package called distance, where you can fit many different kinds of distance functions if you have the exact distances, which is this D column, what we saw in the histogram before. So if you have these exact distances measured to the individuals, then you can fit some kind of distance function to it or do all kinds of model selection. And if you do that, then you can see the true tau that we used to simulate the data was 2, and we estimated 2.17 using distance sampling. If I go back here, we also estimated this using simple GLM. If we knew the non-detections, that's a bit closer, 2.03. So with less data and using distance sampling with the exact distances, we're doing pretty good. So after the break, we are going to see how we can talk about average detection and estimate this parameter when we have only binned data. So we don't really have these exact distances. The distance was 2.32, but we only know distance was greater than or less than 1. And by these units, I mean 100 meter.